Well, good afternoon, everybody, and welcome back to COVID-19 in Context, brought to you by the University of Mary Washington. My name is Anand Rao. I'm a faculty member here at UMW, and I'm excited to welcome you to a really great presentation that's planned for today with a wonderful panel. The topic tonight is COVID-19, the curve, the numbers, and the markets. And we have two wonderful presenters, Dr. Suzanne Sumner, who is a professor of mathematics, and Dr. Rachel Grafe Anderson, an assistant professor of finance. And then they're going to be joined by two colleagues, Dr. Melody Denyer, Associate Professor of Mathematics, and Dr. Jeb Collins, Assistant Professor of Mathematics for the Q&A. Now, before we turn it over to the presenters, I wanted to give you a quick reminder. You have both a chat box, and please keep that just for any comments to myself or Dr. Mellinger about any technical issues that you think are developing. We've been able to solve technical issues fairly quickly when we're able to get feedback from you through the chat box. So please save it just for those comments for the two of us. If you have questions for the presenters, and we will have time after the presentation for a full Q&A session, please put that in the Q&A box. And as you're looking at the Q&A questions, I see one's already posted, look at the questions that are already there, and then get ready to upvote the ones that you want to make sure go to the top of the list. We're never able to get through all of the questions, but we are able to get to the ones that have the most votes. So it's important that you look at the ones that are there, upvote the questions you'd like to make sure are at the top of our list. And we'll get to those first when we get to the Q&A. Now, it's my pleasure to turn it over to the presenters, starting with Dr. Suzanne Sumner, who will be followed by Dr. Rachel Grafe Anderson after her portion of the presentation. Dr. Sumner.
Welcome to this afternoon's lecture, COVID-19, the Curve, the Numbers, and the Markets. We will start today with a presentation from Dr. Suzanne Sumner of the UMW Mathematics Department titled COVID-19, Modeling the Curve, and then lead into a presentation by Dr. Rachel Grafe Anderson from the UMW College of Business about the effects of COVID-19 on the financial markets. I am presenting our Modeling the Curve presentation on behalf of Drs. Jeb Collins, Melody Denyer, Deborah Hydorn, and Wyatt Mangum. With COVID-19, epidemiologists have been using mathematical models, which are mathematical representations like formulas, tables, and graphs that describe a phenomenon's important characteristics. The goal is to find a mathematical model that fits the observed data the best, so we understand the phenomenon in question, in this case, how a disease spreads. The mathematical model helps epidemiologists make predictions so that leaders can make decisions, such as when to close down a state and when to reopen. Ideally, these models can help us find solutions, for example, when to enact social distancing or which populations are best served by a vaccine. The quality of a model depends on the assumptions made in building the model and the accuracy of the information entered into the model. Recall the 2017 solar eclipse. Based on hundreds of years of data collection, NASA could accurately predict exactly when and where the total eclipse could be seen. With COVID-19, we have only had a few months of data, and so much is unknown about the disease that the models are constantly being updated to improve their accuracy. The mathematical models we will demonstrate here today describe the spread of an infectious disease, and the models can be modified in multiple ways to suit the biology of a particular disease like COVID-19. We will make many simplifying assumptions to create a baseline model as a first step, and complications can always be added to the model to be more realistic. The first simplifying assumption we make is that we study a population of constant size, called N, over a short period of time. Short enough so that births, deaths by other causes, and immigration are not factors. Typical examples are children in a school, college students in a dorm, patients in a nursing home, etc. We also assume that the members of this population mix homogeneously, where all population members interact and contact each other to the same degree. The population contains at least one infected individual, and the uninfected individuals face an equal risk of exposure to the disease. We will measure the time discretely by days to simplify the mathematics. Here we have a diagram demonstrating the difference between heterogeneous mixing and homogeneous mixing. The green balls represent infected individuals, and the purple balls are the healthy ones. With homogeneous mixing, the two colors are evenly spread out and not clumped in groups. We will use a compartmental model to create what is called the SIR model of disease spread. In this compartmental model, the members of the population are in one of three possible compartments: susceptible individuals, infective individuals, and removed individuals. And individuals move from one compartment to the next, depending on their current status. We use the subscript T to indicate the time period, which for us will be days. For each day T, ST represents the number of healthy individuals who are susceptible to catching the disease but are not currently infected. IT represents the number of infective individuals who are infected with the disease and currently contagious. In this most basic model, we call this group infective since they are capable of spreading the disease, and for the moment we assume that infected people are immediately contagious. We will change the model later to include an incubation period when exposed people are not immediately contagious. RT represents the number of individuals who become removed from the population because they're no longer able to contract the disease, either by permanent immunity or by death due to the disease. Because of interaction within the population, some susceptible people become infective, meaning that the susceptible compartment will decrease and the infective compartment will increase. Some of the infective compartment will recover or die, so the infective compartment will decrease and the removed compartment will increase. We call ST the number of susceptibles at time T, so ST plus 1 is the number of susceptibles at the next time T plus 1. The number of susceptibles in the next time ST plus 1 depends on how many susceptibles are in the current time, subtracting out the number of people who get infected. The number of infectives at the next time IT plus 1 depends on how many infectives are in the current time IT, adding in the number of people who get infected and subtracting out the number who recover or die. The number of removes in the next case, RT plus 1, depends on how many removes are in the current time RT, adding in the number of people who recover or die. Here we see an example where the total population number N is 500. The initial number of susceptibles is 499, and the initial number of effectives is 1. The initial number of removes is 0. Not every interaction between an infective and susceptible transmits the disease. For this example, we assume a small transmission coefficient, which we call the Greek letter alpha. In this case, 0.001, meaning only a 1 in 1,000 chance that an interaction transmits the disease. We also assume a removal rate, called the Greek letter gamma, to be 1/10, meaning 1/10 of the infectives recover or die. The blue curve shows the number of susceptibles decreasing to nearly 0, and the number of removes in green increasing to about the total population of 500. The red curve is the number of infectives, which is the familiar bell-shaped curve we see describing the number of cases. The number of infectives increases to a maximum of about 253 after about 22 days. The shape of these curves depends greatly on the values of the transmission coefficient alpha, the removal rate gamma, and the initial numbers for each compartment. These two graphs show how to reduce the size of the infective peak by reducing the likelihood of a contact transmitting the disease, say by exercising social distancing, wearing a mask, and using hand sanitizer. Lowering the infective peak is called flattening the curve, where the idea is to practice social distancing and other protective measures to bring the peak below the level that our healthcare capacity can sustain. Say the number of ICU beds and the number of respirators. Notice, however, that flattening the curve also means that the peak occurs later because the time since the first infection increases and the disease lasts longer. Here we can compare the new COVID-19 cases for multiple countries as of June 24th, 2020. Real data tends to have a fair amount of variation, so this graph shows a rolling 7-day average so that the trends are easier to identify. This graph shows that the countries greatly affected by the pandemic, like France, Italy, and the United Kingdom, appear to have promising downward trends. However, the curve for the United States does not have the characteristic bell shape, and the trend in new cases is upward and truly troubling. Researchers often refer to a value called the basic reproduction number, R0, or R0, as a measure of how infectious a disease is. R0 represents the number of new infectives created by a single infective over the course of the infectious period. R0 is calculated to be the product of the number of new infectives caused by a single infective per day times the average duration of the infectious period. So R0 is the transmission coefficient alpha times the initial number susceptible 0 times the average duration of the infection, which is what we call 1 over our gamma. When R0 is greater than 1, the number of infectives increases and an epidemic occurs. When R0 is less than 1, the number of infectives decreases and there is no epidemic. For our earlier example, R0 is almost 5, which indicates a severe epidemic. The World Health Organization estimated the R0 of COVID to be between 2 and 2.5, meaning an infected person is expected to infect between 2 and 2.5 people while infectious. However, contact tracing has determined incidents where one person was responsible for many more than 2.5 infections. This CDC slide describes the Mount Vernon, Washington Inquirer case where 52 people were infected by one person. In South Korea, patient 31 had contact with 1,160 people, leading to 5,016 infections at her church. The basic SIR model is an idealized model with many simplifications. Let's return to the assumption that an infective person is immediately infectious. If we assume a lag period between when a person is exposed to a disease and when they become infectious, then the model becomes an SEIR model, with an additional compartment for an exposed class who are exposed to the disease but not yet infectious. Most COVID-19 models are SEIR models. The SEIR model is similar to the SIR model with a new term beta called the contact rate that represents the fraction of contacts that result in exposure to the disease, which takes the place of our earlier alpha. The exposed compartment equation, ET plus 1, is the number of exposed at the next time t plus 1, being equal to the number of exposed ET at the current time, adding in the number of susceptibles who became exposed, and subtracting the number who become infectious. The number of new infectious people are then moved into the infectives compartment. The two graphs show the difference in the shape of the curves for an 8-day incubation period compared to a 2-day incubation period. The exposed population in orange has a narrower peak, and the infective population in green has a higher peak when the incubation period decreases from either 8 days to 2 days. For comparison, COVID-19 has an incubation period of 4.8 to 6.5 days, so its graph would lie somewhere between these two pictures. We've included a link to a Google document with additional resources. For the brave of heart, we have additional slides at the end with more details on the mathematics. Let's turn now to an epidemic calculator at this link so we can study the effects of changing model parameters. Then Dr. Grafe Anderson will present her lecture on the effects of COVID-19 on financial markets. So this model here uses some what we call a continuous time model, which is a little different from the discrete time model that we talked about. This would require some use of calculus, and so that's why we didn't discuss that. But the model is very similar. It's an SEIR model for COVID-19. And at this link, we can do things such as adjust the basic reproduction number. So since COVID is somewhere between 2 and 2.5 in its basic reproduction number, you can see the effect of the different categories: susceptible, exposed, infectious, etc. So exposed are in tan, infectious are in pink, Hospitalized and fatalities are in the blue colors. We can also see what would happen if the duration time that the patient is infectious is increased, and see how that increases your numbers of exposed, infectious, and hospitalized people. We can also change the recovery times and see the effects on the curves as well. So what's nice about this website is you can experiment by changing the different parameters to see the effects that it has on your epidemic curves. Thank you for your attention, and we will turn it over to Dr. Grafe Anderson for the effects of COVID on the financial markets.
Thank you, Dr. Sumner. We appreciate that. She made reference to a Google Doc with other additional references. We'll put that in the chat box shortly as soon as we're able to get that from the slide. Next, we'll turn it over to Dr. Grafe Anderson to continue with the presentation.
Thank you for having me. I'm happy to be here with you all and to be following such an excellent explanation of the mathematics behind COVID-19 modeling. I'll shift gears here and present a fairly big picture view of financial markets under this pandemic. Numerous studies have already been completed on the impact of the pandemic, and it seems safe to say that it has caused unprecedented global economic damage. We simply don't know how much yet. Of course, regarding the financial markets, one way to sum it all up quite succinctly would be to say, the financial markets, they're all over the place these days, and leave it at that. But I'll provide a little more insight into why that is happening and what it means. Quite generally, we consider stock prices to be a reflection of two things. First, current expectations of what we call future cash flows, and two, the risk associated with those cash flows, which translates into a desired return on investment appropriate to the level of investment risk. To elaborate on this, a firm's operations generate cash flows. Some of this is spent by the firm on day-to-day operations and long-term investments. The remaining cash flows go to the firm's investors, both creditors and shareholders. The stock price is, thus, a reflection of what cash flows shareholders expect the firm to generate, and then also what their share of those cash flows would be. The stock price should also reflect how risky the stock is considered to be. That risk will include what we call firm-specific risk as well as overall economic risk, which we often refer to as market or systematic risk. Firm-specific risk would include any risk to which the firm is susceptible due to its own specific attributes, such as the risk that employees would strike. Some companies, such as airlines, are more susceptible to such a risk than others would be. Market or systemic risk involves those risks to which all businesses are exposed, such as the occurrence of a pandemic. So generally, when one or both of these things, that is, expectations of future cash flows or the riskiness of the investment, changes, then the stock price would change accordingly. As a basic example, consider when publicly traded companies announce their earnings each quarter. These earnings can be an indirect indication of the firm's cash flows. During the period leading up to the announcement, expectations are formed about what the earnings value will be. When the earnings are announced, if they are lower than expected, investors adjust their expectations of future cash flows downward and thus value the stock at a lower price. This leads to selling of the stock, which causes the stock price to go down. On the flip side, the opposite happens if the earnings are higher than expected. So, what is happening under COVID-19? Well, both of these elements to stock price are changing and doing so rapidly, and nobody knows by how much. On the one hand, all economic risk has increased, but some companies are more vulnerable than others. On the other hand, the pandemic has led to a rapid flow of new information that cause rapid updating of expectations of future cash flows, both upwards and downwards. Simultaneously, other global economic events, such as the tussle between Saudi Arabia and Russia over oil supply and prices, continue to impact the market as well. To sum up, we are in a period of massive upheaval and uncertainty, we can all agree, and stock price changes and volatility in the financial markets is simply reflecting that. Let's step back and take a look at what has happened in the financial markets. Back in February, the financial markets had a rather mild response to news coming out of Wuhan, China, about the potential for a large supply side shock. A lot of manufacturing is done in Wuhan, so the disease was expected to disrupt this and cause certain shortages that could disrupt other businesses that rely on those products. I distinctly remember because my student managed investment fund students began to incorporate this news into our class discussions. But in the US and Europe, the big market reactions happened in March, when COVID-19 was declared a pandemic and governments began to get very serious about shutting things down. In March of 2020, the US stock market hit the circuit breaker mechanism 4 times in 10 days. What does that mean? When the stock market crashes very quickly, the circuit breaker halts trading temporarily to prevent a complete collapse and allow time for things to settle. This is because frantic trading can cause a collapse that would not reflect the underlying company values accurately, but would be very difficult to fix. To put it another way, what happened in March is that the world realized the pandemic would create simultaneous and large demand and supply shocks, which would have massive economic impacts on businesses due to country, state, and provincial shutdowns. While these shutdowns will cause some firms, even very large publicly traded ones, to fail, it is unreasonable to think they all will fail, which is what a complete market collapse would suggest. But back to what happened, the S&P 500 index, which is usually used as an indicator of financial performance in the US, crashed 30% from its high in February. The FTSE in the United Kingdom fell over 10% in one day on March 12th. In Japan, the market fell 20% over the course of the month, and many other markets had similar reactions. These crashes were met by Federal Reserve and other central bank action. The Federal Reserve injected capital into the markets through something they call quantitative easing, which is essentially large purchases of long-term Treasury securities. The expectation is that these purchases, which are made from other institutions, will increase the capital those institutions have then to lend to businesses. At first, the quantitative easing program that was announced had a cap at around $700 billion, but the market response to that was mild, to say the least, and not necessarily positive. So the Fed eliminated the cap. The Federal Reserve also cut interest rates such that they remain at near zero and almost negative levels. Similar actions were taken by other central banks. The European Central Bank also maintains low interest rates and has relaxed restrictions on lending by allowing for more flexibility in how we define collateral. This is a chart of the S&P 500 index from March 1st to July 1st. You can easily observe the dramatic decline in March, followed by a strong recovery. However, that recovery is marked with substantial ups and downs, indicating high volatility. Furthermore, the recovery does not go all the way to the peak from February 2020, and we can expect continued ups and downs going forward due to continued economic uncertainty. Much more recently, the jobs report for June was far better than expected and has created a market surge as investors have hope that this indicates the economy itself is heading into a recovery. Usually, economic recoveries are preceded by financial markets. And again, this is because prices in financial markets are based on expectations of future outcomes. Of course, this recovery is also propped up by the measures being taken by the Fed, and no one really knows what will happen if the Fed halts or alters their quantitative easing policies. The main drivers of all this uncertainty are, of course, the various manifestations of depressed economic activity due to state, provincial, regional, and country shutdowns. Unfortunately, what we see happening recently is a resurgence in COVID cases after states in the United States began to relax their restrictions. As the COVID cases tick upwards again, states are reversing course and reinstating shutdowns. This is particularly harmful to the service industry. We have already seen that many small businesses have failed or likely will fail if states go into a full lockdown again. Those business failures create more lost jobs, so it will be interesting to see what the July jobs report looks like. Furthermore, it will be interesting to see what the economic impact on the US will be now that our citizens are restricted from traveling to many countries around the world, which is also a recent development. As for risk, we usually measure market risk by measuring the volatility of market prices or of an index such as the S&P 500. We measure volatility as the standard deviation of daily prices in the market. In the United States, a recent study has documented that volatility nearly quadrupled for the month of March. The same study also shows marked increase in volatility in many other countries, including Italy, Spain, Germany, France, South Korea, Japan, and Singapore. So the bottom line is that we see a dramatic increase in risk overall, which is not unexpected under the circumstances. What is interesting to add, however, is that the correlations between market returns in different financial markets, delineated by country or region, has also been changing. This indicates a change in the way the global economy interacts and the nature of the systemic risk in globalized financial markets. Interestingly, the same study mentioned before has found that in late March, these correlations began to cluster regionally, with the US and European markets remaining highly correlated with each other, but less so with Asian markets. This development could be a result of differences in countries' approaches to and efficacy at managing the pandemic. Another recent study found a strong negative stock price reaction to increases in confirmed cases of COVID-19, but no relation between stock price reactions and increases in deaths. So it may be that as some countries begin to control the rate of spread more effectively than others, their markets will strengthen more quickly than those countries with a higher rate of spread going forward. And these correlations will continue to diverge based on how these countries are handling the pandemic. But bottom line, ultimately, no one really knows what's going to happen. This is generally true about the pandemic, and economic activity and the financial markets will continue to be very volatile and have their ups and downs over the coming months. They will surge when we have good news that indicates improvement in how we're handling the situation and improvement in economic conditions. And they will fall again when the news is negative on those two things.
Well, thank you so much, Dr. Sumner and Dr. Grafe Anderson, for the really informative, great presentation. There's so much great content there. And we have a number of really wonderful questions. The presenters will be joined, as I mentioned before, by Dr. Jeb Collins and also Dr. Melody Den here for the Q&A portion. I want to start off the Q&A with a question directly for the last presenter, Dr. Grafe Anderson. It has to do with questioning why the stock market is so high. There seems to be such a disconnect between economic indicators referencing economic recession or potential collapse in different sectors, increasing levels of unemployment and a lot of volatility, and yet the stock market keeps going up. So the question is the stock market being manipulated? Are the markets manipulated? Is it just the rich selling to the rich while they're out of touch with the rest of the economic indicators?
Yes. Well, hello, everyone. And I'm happy to do my best to try to answer that question. And I noticed there were a few questions that were similar in nature as well as follow-ups. So when it comes to the stock market, it tends to be optimistic in general. Hope usually beats fear in the stock market. Not always. As we've seen, sometimes fear takes over and we have a crash. But whenever there's some sign of hope, it usually results in a quite substantial rebound. On top of that, there could be some manipulation going on. Certainly there is. The markets are not functioning fully independently here. Right now we have government stimulus money that's been injected into the market to make sure that the businesses don't go under. We also have the Fed injecting money through quantitative easing into the market to make sure that that capital is available. And so that's all propping up the market. So I don't think it would be nobody really knows if the financial market is currently at a bubble right now, but it would not be unreasonable to ask that question, because we don't know what happens when the government starts changing their policies and easing off all of this assistance that it's currently providing to those markets. But I will just add or reiterate that also the crash in March was generally viewed to be an overreaction. Whenever there's an overreaction in the market, you do see a correction occur. So some of this rebound we would have expected to see, perhaps not as much as we've seen. And it's also, of course, been up every time there's good news that comes up and down every time there's bad news that comes out. And I saw another question about sort of what might happen if the cases keep going up in the US. I can only speak to my opinion on this, my educated opinion on this, but I think it would generally be a pretty bad sign for our financial markets going forward. And if anybody else would like to weigh in, feel free, fellow panelists.
Thanks for that. I'm not sure if I feel better about my stocks or not. I don't know, but thank you for that. Hi everybody. Keith Mellinger here, Dean of Arts and Sciences, and I want to turn to some more questions here for the mathematicians as well. Whenever we try to model the growth of a population in some way, in this case, modeling the growth or the spread of this disease, there's of course impacts on other populations as well. And while some of us may expect that that birth rates are going to be affected in some way, that we might guess that the population of is actually going to decline because of this pandemic, but maybe that's not necessarily the case. So maybe I'm going to turn to Dr. Sumner maybe first. If you can say anything about how modeling one of these things can affect the modeling of other things, like for example, the birth rate.
That's a really great question. I saw that in the Q&A box. I'm Dr. Sumner, by the way. And there was an article recently in the New York Times. It came out on April 8th, and that was a question that people had, so they decided to answer the question, because often when there's power outages, you will often see 9 months later a baby boom, and so they were wondering if social distancing and quarantining at home would have the same effect. And it turned out that no, actually people are very concerned about the economy and the uncertainty of the future and the uncertainty of the disease, and most people are not feeling comfortable choosing to have a new child at this time. So they're not seeing the baby boom that they were expecting from that. And then I don't know if any of the other panelists have an opinion on that or not. So.
Dr. Mellinger. The one other comment that I have on that, by the way, I am Dr. Collins from the mathematics department. I do know that the CDC has recently come out with some guidelines for women who are pregnant that essentially says that they are in a higher risk category if they are to get COVID-19 if they become pregnant. There is not, I don't believe they have put together a risk of the baby contracting the disease through utero, but a pregnant woman is at a higher risk of either serious complications or other health risks happening if she gets the disease while pregnant. So that could be yet another reason why a baby boom is not necessarily going to be occurring through this.
That's great, thank you. It's interesting when we're looking at those models, population models, of how those factors play in with one another. You know, there's the next question that I have is a really interesting one that combines both the mathematical modeling for populations and the spread of the disease with financial markets. And it's the comparison between the United States and Sweden, or some of the other countries and Sweden, and the attempts, maybe even better, to compare some of the other European nations with Sweden. in that they took very different approaches. And some of us have heard of this in the news, that Sweden decided not to implement the same restrictions as other countries, with the hope that perhaps if it spread a little faster, I don't know if it was the potential for herd mentality or herd immunity, or perhaps for their ability to be able to handle that immediate bump, that big curve, and then move beyond it. But some reports are coming out suggesting that Sweden was not effective in that they had that big curve, they weren't able to flatten it, and yet even though they've gone beyond it a little bit, they've still suffered economic repercussions. So the question is framing it as, it looked as though whether or not they were trying to flatten the curve, they still suffered economic complications and consequences to those actions. So turning it over to probably the mathematicians first, and then to Dr. Grape Anderson. How should we consider the use of those mathematical models to look at flattening the curve? Often we talk about flattening the curve in terms of public health. How important is it to think about flattening the curve and tying that to a financial model?
I seem to be the one with a live mic, so I guess I'll go. You're right. The case of Sweden has been a very interesting case. They were hoping for herd immunity, and the idea in herd immunity is that a large number of people in the population get the disease, become immune ideally to the disease, and then are no longer able to spread it, and or you have a vaccine which raises people to that same level. And then that way you can protect the people that are the most vulnerable, the people with weakened immune systems that may not be able to get a vaccine. And so it turns out that the herd immunity threshold is related to the idea that basic reproduction number, you take your R0 minus 1 divide by R0. And so for COVID ranging from 2 to 2.5, the herd immunity threshold would end up needing to be about 50 to 60%. What's been unfortunate is a new study that came out about in the last day or so about Spain, and Spain was able to measure COVID antibodies in about 5% of the population. So they're not at the level, a country like Spain is not at that level, and I don't remember what Sweden's numbers are, but they're wondering if that was maybe not a good strategy after all. And I noticed one of the other questioners mentioned that immunity is not clear for this particular disease, COVID-19. And as it turns out, some of the models in question are not just SEIR models. The one that Harvard is using is an SEIRS. So after the removed category, you have immunity for a short period of time, and then you can go back to being in the susceptible category again.
So I'd like to follow up on that, and maybe to Dr. Collins, maybe to speak a little bit about this modeling, because Dr. Sumner made reference again to the SIR model and the expanded model that she talked about in her presentation. But how simplified is that? I mean, is that typical to try to simplify it to that level, or do we typically, when we're trying to model something this complex, are there usually a lot more variables involved? Is it always start with something simple like this? How does a mathematician approach modeling something that can sometimes be this complicated?
So, Dr. Mellinger, that's a great question. And I think one of the things that is maybe not necessarily known about how mathematicians go about attacking big problems like that is that, yeah, we start off as simple as we possibly can. For the main reason that that's the easiest thing to do. That's the way that we can start to get a grip on the problem. And then it's fairly easy to then add on things. For instance, just like Dr. Sumner noted, we had the SIR model, and then we were able to add on another compartment for exposed populations. And if you look at the app that she had at the end of her talk, they added on hospitalized, they added on, they kind of broke up the R into fatalities and recovereds. And so it's very easy once you have a basic model to then start to complicate it further and further. The other thing is the SIR model is not incredibly basic when you really take a look at it, because the hard part is getting those numbers. What is the infection rate? You know, really, that's represented by one number in that model, but how do you get that number based on the data that you have, and how do you try and get that number as exact as possible? And this is possibly where Dr. Denhier can talk more about it, because it is heavily involved with statistics and trying to take the incredibly limited amount of data that we have and try and use that data to obtain as accurate a number as we can for how infectious the disease is, or how quickly you move from infective to recovered. And that's one of the problems with modeling this, well, modeling anything really, but especially a novel disease like this, is there's just so little data to work from. And especially when some of the initial models were coming out in March and early April, there was far less data to work from. And the models were always changing because they were trying their best and using some of the most advanced mathematics they could to get accurate numbers from a very limited amount of data. But to your original question, Dr. Mellinger, yeah, this type of model of moving from one state to another is a very common type of model. It allows you to kind of describe the population in a very general way. And then, like I said, it can always be complicated. You can always add more states. And especially like Dr. Sumner just said, you can loop it around again if, for example, immunity is not really shown to be permanent.
We might try to start with a simple model, but it gets very complex very quickly. As you've identified, there are a lot of factors there to consider. The next question is an application of some of what you were just outlining, in particular talking about cases in states where they've seen a real resurgence of cases, something like Florida, for instance, where they've had a big increase in the number of cases. How difficult will it be for them to get it under control? Will the models be able to make those predictions? And, you know, I wanted to add a little bit to it if perhaps Dr. Sumner wants to start with that, but then also if Dr. Grafe-Anderson could speak to how markets might look at those models and look at those, because you made reference to the idea that financial markets certainly are aware of cases, and that they see an increase in the number of cases that could be factored into financial market decisions. Are they looking at individual states? So first, Dr. Sumner, the original question about, are they going to be able to get it under control anytime soon? Is that something that the mathematical models could predict?
So I see in the question answer, the state in question was Florida. And in the chat box and also at the end of the PowerPoint, we have a link to a Google Doc. And one of the links goes to a COVID-19 simulator where you can look at a state-by-state level. And if you go to that and go to Florida, and I'll see if I can, I don't know if I can share my screen. We'll see. Okay, can y'all see that?
Yes.
Okay, so if we go to Florida, the question was Florida in an exponential phase? This is the cumulative number of deaths in Florida. If you look at the number of new COVID-19 cases, it's starting to get what we would call an exponential shape, which would be increasing and curved up. And then if you look at number of active cases, they have some predictions. Number of hospital beds, they're fine on hospital beds, but there's going to be a real problem with total ICU beds and available ICU beds, that they're going to have a lot of difficulty if things continue the same way that they're continuing in Florida. And so the question is, you know, should we be looking at this in a state by state? And one questioner said, should we even be even more local than states based on the Spanish flu in different communities. I've heard a lot of epidemiologists say the more detailed you can get with your information, urban areas versus rural areas, areas near prisons, near nursing homes, etc., that the more local you can get, the better. Of course, that means you need even more and more and more data, which, you know, as Jeb had said, means that you have, you know, quite a bit of information that we need to gather, and it's so hard to get that information.
So Dr. Grafe-Anderson, then following up with that, how closely do the markets look at individual states and the concern about whether it's an exponential increase of cases?
So there's been no indication that the markets have necessarily responded to more than simply the speed of the spread does seem to be negatively correlated with stock returns, but it does not seem to have any sort of regional or local you know, basis. So the fact that if Florida, part of the problem is that this country is very diverse and very large, and there's a lot of variation in the behavior and responses all throughout the country. That is something that sort of distinguishes this country from a lot of the other countries that have much more uniform approaches to the pandemic. And so, you know, the bottom line is if you can't get your business done in Florida, you can probably still get it done somewhere else. So the financial markets aren't going to be necessarily focused on Florida. Said, if the economic impact in Florida is serious enough, then there will be a financial market response to that. So it will really depend on how bad the economic impact is in any particular location, and whether or not that could be offset by economic gains in other areas where maybe the problem has, you know, has sort of stabilized. And just to go back for a second, just to the Sweden thing, because I didn't get in on time, and before the follow-up question, I just wanted to make a note that part of the problem for Sweden's financial markets, you see, if you actually take a look at a stock chart of their sort of an index in Sweden, it looks very similar to the S&P 500 chart that I showed in my presentation. Same shape, same timing, everything. And that goes back to all those correlations. All these markets are so highly correlated that even though country by country, you may be taking different approaches, all of these economies are just intricately linked, and the markets are highly correlated. So they just can't, they wouldn't be able to escape that. Yeah.
All right, thank you. I want to turn to a question about the parameters that we use in our modeling. And so maybe I could start with Dr. Collins on this one. You know, there's a lot of parameters that Dr. Sumner discussed when she was giving the presentation. Parameters that define the spread of the disease, and those parameters could change depending on the disease. And of course, this is the novel coronavirus. This is the one that nobody knows enough about yet, right? So we're still studying and trying to understand what those parameters are. But can you talk a little bit about things like, for instance, immunity? Like, if we don't really understand completely immunity yet. There was an assumption early on. I remember reading something that once you recover from this, you're good. You're good, you know, for the rest of your life. You're good, right? And we are starting to hear more and more research about immunity. But as we learn more about these parameters, things like immunity, how does that affect the model? How does that change? How many different parameters could there be for something like this?
Yeah, so the parameters are really, I think, where the key is. The models, I mean, I don't believe they really get a whole lot more complicated than what Dr. Sumner described. It's a bunch of states, and you move from one to the other just by, okay, you're susceptible, and then a certain number of susceptible people move on to becoming infected, or whatever the next state happens to be. But yeah, trying to figure out that particular number is is the key, is really the hard part. And that's honestly where you start getting into data science, and trying to take the data that is being recorded and turn it into a number that can be put into a computer program that can be run on one of these very simplified types of models to try and tell us something about what's going to be happening in the future. And so there are a lot of different methods for trying to take the data. So for instance, one of the things might be the fatality rate. I think that's probably one of the biggest numbers and parameters that people know so much about. So how many people are going to die from this disease? And one of the biggest problems with that is we don't know who actually has the disease. All the testing is being heavily biased towards people who get very sick from the disease. If you are asymptomatic, or if you just have very light symptoms, certainly at the beginning of all this, you were told to stay home and don't even get tested. If you have a fever, maybe get tested, or maybe just stay home for 14 days and save the tests for those who are frontline workers or who really need to be tested. And so a lot of our bias was on those who were of high risk and were more likely to die from the disease. And so when mathematicians try and figure out what the actual fatality rate is for the disease so it can be plugged into our models, we have to take that bias into account. And we have to somehow use some of our tools to say, okay, well, the data is obviously heavily biased towards people who are more likely to die. So somehow we need to, when we estimate the parameter, undo that bias in order to get what is hopefully a more accurate measure of the fatality rate for this disease. And that type of trick is played for all different types of parameters. The infection rate, how likely is it for someone who is sick to need to be hospitalized? Each one of these, moving from one state to another, has its own little parameter to it. And so as complicated as the model is, that tells you how many different parameters need to be estimated.
So as you're explaining that, I think you're touching on a couple other questions that we have in the feed that I kind of ask as a follow-up. And I think you've been able to help disentangle this, that there are a lot of different variables and factors that have to be accounted for. For example, you mentioned hospitalizations. That's a question that was raised in the Q&A feed about how proportional that is to the number of people that are infected, and whether or not that might vary dependent upon the population that's infected. So that if you read tragic cases of number of cases going through a nursing home, and the percentage of patients that succumb to the illness, that die from it, is a higher percentage because of pre-existing conditions. So varying populations will factor into it as well. But then it seems like testing is a crucial component of this. I mean, it just seems that as you start to unpack this, it gets more and more complex about how you're able to control for this. Maybe the way to ask it is this, because each of these questions is looking at it as, okay, it seems like this is a variable that we can't really nail down. As a mathematician, what would you like to have in terms of data referencing the spread of this disease to be able to give a better model?
As a mathematician, what I would like to have is I would like everyone to be tested every single day. And I would like perfectly accurate data from every hospital in the world. As a mathematician, I want the truth. And I want to be able to put that truth and put it into my model, and then my model will be able to tell you the truth of what will happen tomorrow. There's a famous quote, and I can't remember the full quote itself, but it starts off with, all models are wrong. Some models are useful. And I think that's one of the key things to keep in mind as we are, as a society, now currently obsessed with mathematical models, which we probably never would have thought we would be 6 months ago. But the models are all wrong. The models are not meant to accurately reflect what the reality is going to be like 6 months down the road. It's not meant to accurately reflect the total death count or the total number of infected that will be at the end of all of this. The The models take the data that we have and try and give as best an approximation as possible, given both the data that we have and the simplicity of the model. The idea is that we are sort of treating people as particles of gas in a box, and not taking into account the fact, for instance, that everyone might be socially distancing, but even with socially distancing, a large portion of our population are all going to the same grocery store and touching the same, you know, maybe a large portion of the population are interacting with the exact same grocery store clerk. So you might be very well socially distancing from everybody, but because you're an actual human, you know, there are certain characteristics that are just go along with that are not being accounted for in our models. Dr. Sumner's beginning of her talk really talked about how we are assuming that it is a homogeneous system and everyone's just kind of equally distributed. And that's just not the way the real world works. And the real world is just far too complicated to model mathematically. We do the best we can, and we try and fudge the parameters to try and accurately reflect the real world, but there's a certain level at which the real world is just far too complex to model accurately. I would always like more data. Obviously what I was saying was impossible, but I would always like more data, because the more data I have, the more accurate my parameters are going to be and the more accurate my model is going to be.
To expand on this even further here, the models, we've seen lots of models come out from different sources. There's a specific question in the Q&A about a model from UVA. Can any of you comment on your feelings about the models that we've seen come out, and if you think that those are particularly good or bad? Maybe start with Dr. Sumner.
I see two questions, one about the UVA model and another about the our world and data. So the UVA model, just for full disclosure, University of Mary Washington was once the sister college to UVA. So we are going to say that we love UVA and their model is excellent. The UVA model is using an SEIR model, as we talked about at the end of my presentation. So I would have good confidence in that model. Someone asked about the R world in data, and that's from the University of Oxford. And she or he is asking, how should we judge data sites and their background, etc. So a really quick way that you can judge a source of information is to type in the source of information and then right after that, Wikipedia, and see what Wikipedia says about that particular source. And they'll let you know if it's left-leaning, right-leaning, if it's a valid source or not. Wikipedia in general does a pretty good job of judging sources of information. So that's just a little bit of advice I would give.
Thanks for that. Dr. Rao, we're running out of time here. Do you want to ask one more?
Sure, I think there's probably one more here that we could fit in. A question of when we're looking at the models and how we make policy decisions based upon it. If we're seeing the numbers rising and falling, what's the best way to react to this? Is it a matter of a complete lockdown? If we're seeing the numbers rising, can we take more temperate actions? How do we apply the models for the next policy decision when we see an increase?
There is a YouTube video that Dr. Collins found and added to our Google Doc. And it was one of the suggested readings, even though it's a video. And it's a 23-minute video, but they simulate and do a really good job simulating all of the different combinations of things that you could do. What if you could identify people who are infected and quarantine them? What if you have everybody going to a central location like a store, like Dr. Collins had mentioned? What if you practiced good hygiene, right? And so one of the things that you can do with simulations is you can try out a bunch of different things and then see what would happen. And it's a lot easier and more ethical than trying it out on an actual population. And so we highly recommend trying simulations and looking at that particular video.
All right, thank you very much. We're about at the end of the hour here. Thank you all for this. This was very enlightening. Dr. Rachel Grafe Anderson, Dr. Suzanne Sumner, Dr. Jeb Collins, and Dr. Melody Denary. We really appreciate your presentation today. This was an important part of this course, understanding the mathematics behind all of this and the financial markets. Looking ahead a little bit, next week we have two terrific presentations coming up. One is on live events. So we have our department heads for music and theater and studio art, as well as the director of the Philharmonic and a faculty director in the Department of Athletics, Health and Physical Education as well, because live events have really been affected by this pandemic. And then we have an exciting talk on Wednesday as well, focusing on inequality. Viruses don't discriminate. And we have a number of faculty from sociology and anthropology, as well as one of our colleagues from the College of Education joining us for that. So lots of good stuff coming. A reminder to the students, you do have the final paper coming up, and I did post a document in Canvas that'll give you more details on that. It's in the announcements, but it's also just in the files section of the Canvas course. So please take a look at that. And if you have questions, feel free to contact either myself or Dr. Rao with your questions. So until next Monday, thank you all so much for joining us for COVID-19 in Context. It was another great week. We have 2 more weeks of the course left, and we'll look forward to seeing you next Monday. Thank you all.
Thank you. Thanks for having me.